Hello everyone, my name is Mustafa Alperen Gürbüz and this is Lab 6 Magnetic Braking with Faraday, and it's the lab for Georgia Tech 2212 Physics 2. So here's just a table of contents I'll be going over. I'll first go over the introduction, the details of the variables, the details of the experiment, the code for the computational, the extension of the code and possible errors, and answering what if or what else. So the purpose of this lab is to observe the behavior of a magnet falling down in an aluminum tube and comparing it with the aluminum computational models we do on GlowScript. So some fundamental physics principles is Faraday's law, which states that in a conductor, a changing electromagnetic field creates an electromotive force, commonly represented by EMF equals delta flux over delta T. In the Biot-Savart law, a steady current creates a magnetic field around it, which is those two equations. I'm not going to read them out because they're very long. So a brief preview of the main results is just that the time spent in the tube in real life on average was around 1.33 seconds, and the time in the tube computational was 0.911 seconds. So details of variables. For the models, we use the velocity versus time graph. For assumptions, we assume that we had negligible air resistance. The bar magnet could be considered a magnetic dipole, and only forces being applied are magnetic and gravitational. And the system and surroundings. The system is the aluminum tube as well as the magnet that's falling down, and the surrounding is everything else except those two things. So the details of the experiment. Our initial conditions consisted of the mass of the magnet being 0.023 kilograms, aluminum tube length being 0.5 meters, width of the foil being 0.01 meters, tube's inner radius being 0.03 meters, and the magnetic dipole moment from lab 3 being 5.98 amps times meters squared. And you can see our experiment data over there. It was 1.5, 1.36, 1.31, etc., etc. And the overall average was 1.33 seconds. And there's just a quick photo of me and my lab mates doing the lab. So here's the code for the computational section. So you can see in the top left, in the first part, I just go over the geometry of the tube. Length is 0.5, width is 0.010, inner radius is 0.030. All of these are derived from the initial conditions I mentioned to you previously. And then in the second part, we just define the properties of the magnet. Mass is 0.023, mu magnet is 5.98. Again, we got that from lab 3. That's our value from lab 3. Then we visualize the bar magnet by making a cylinder, and then we define the dipole of B as a function. You can see that there, R mag, R hat, and then use B, Biot-Savart law for that calculation of B. And then we define, calculate df lux dt analytic, and you can just kind of read that over there as I'm talking. But we calculate the speed, distance, and the radius of the ring, and then calculate numerator, denominator, and df dt is just going to be those two divided. And here's just the extension of the code. I know it's going to be kind of small and hard to see the left side, but that's really all I could do. So it's just going to be me. It's like while bar's position is below a certain thing, repeat this, do this, etc., etc. And you can just see it follow down. And in the top right, that's the actual result we get from our glow script. So you can see the graph. And in this graph, again, the time was 0.911 seconds in the computation. And the difference is that it was 1.33 seconds in average in real life. So there's clearly some sort of difference that's being caused here. And so some possible sources of human error that I thought of, is just human error, that being the timing that we're measuring with, or what we drop it and how we're holding everything, stuff like that. There could also be other magnetic forces from other electronics around the area, such as phones, computers, as we did this in a place with a lot of computers. Maybe that's affecting it. That's why the computation is so far off the in real life. And what if or what else? What if the resistivity of the conductor was reduced to as close as zero as possible? How would the dynamics of the falling magnet change? A decrease in resistance would lead to an increase in voltage from V equals I our Ohm's law. This means that the force opposing the fall of the magnet, would be greater and the velocity of the magnet as it falls would be slower. What if holes or slots were cut into the tube? How would this affect the ring currents in our model? There'd be less magnetic force due to there being less currents from our rings. And that's it. Thank you for listening.